Okay, we're going to start to test the endpoints of our radius of convergence to see if they are also valid to determine the convergence of a power series. The first test we're going to look at has to deal with what it's called an alternating series. So we want to understand the process and thinking behind the alternating series test. And in this particular case, when we truncate a series that's alternating, we will know how accurate our estimate is, or at least put a bound on how accurate our estimate is. So that's kind of a neat deal here. I want you to understand the thinking process behind that. Alright, so we left off using the ratio test to determine a radius of convergence. An open interval that's possibly all real numbers. It could be a subset of the real number line, and it also could be just the center. It's really the one that's an open interval that's a subset of the real number line that we're interested in, because that's where we want to test also endpoints. Alright. Here's an example. We've seen the series for arctangent x a few times. It's odd powers of x divided by the same odd power in the denominator, and the series alternates between positive and negative terms. If we did the ratio test on this, and we might have in class, I don't remember, as an example, but if we did the ratio test, we would get a radius of convergence of 1 unit. So since the center is 0, we could go 1 unit in either direction and get convergence. Negative 1 to 1 open would be the guaranteed interval of convergence. It's also possible that negative 1 to 1 may work, and they need to be tested separately. So how do you go about doing that? Well, we first start by plugging in those two values for x and see what series comes out. If we plug in x equals 1, we will get the series negative 1 to the n times 1 to the 2n plus 1. And that's always 1 over 2n plus 1. So it's really this series right here. Negative 1 to the n over 2n plus 1. And if we plug in x equals negative 1, we obtain negative 1 to the n times negative 1 to the 2n plus 1 over 2n plus 1. And if you combine these two terms, because they're the same base, we can add their exponents. We get negative 1 to the 3n plus 1. With a little more simplifying, this becomes negative 1 to the n plus 1. So these two series are just about the same. One of them starts with positive terms, the other starts with negative terms. Okay? In a little while, we'll develop the criteria to test these two series for convergence, because these are both what are called alternating series. So, what is an alternating series? An alternating series has this form. Okay? You'll see a flipper times some expression that contains n's. Okay, so the flipper is necessary, or a flipper needs to be able to develop out of the series. We've seen an example of cosine of pi times n being really a flipper in disguise. Okay, but you need a flipper, and then your expression that contains n's. Okay, now let's take a look at some examples of alternating series. This first one I think we've discussed before. It's an alternating series of 1s. So 1, then a negative 1, then a 1, then a negative 1, etc. Okay, so basically just a series that contains the flipper. The a sub n in this case would be just a constant 1. Now, let's take a look at the partial sums of this sequence and see what they're doing. Okay, so the first sum, s sub 0, is just the first term, okay, which is a positive 1. The second sum is 1 plus a negative 1, which is 0. The next sum is 1 plus negative 1 plus 1, which sends us back to 1. And we can see what's going to happen here in this pattern. You're going to bounce back and forth between 0 and 1. Every other sum is going to be either 0 or 1. And this sum does not converge. It diverges because it oscillates back and forth between two values. It does not approach one finite number. So this is an example of an infinite alternating series that diverges. Now, let's take a look at what is necessary for an alternating series to converge. And I've tried to create a little graphical picture here for you that I think suggests what has to happen here. So we have the arctangent series that we just looked at a second ago. I'm going to plug in 1 in for x, and you're going to see what happens to the numbers that that series creates. Okay, the first term of the series would be a positive 1. And what you're going to see graphed on this number line are the partial sums. This red ball is going to move and be each partial sum. So the first partial sum is just the first term. Okay, so far we're at 1. The next term is a minus 1/3. So if we add that on, our second partial sum puts us at 2/3, or 0.67 if we round. Then we add on a fifth. That pushes us back to the right and puts us to 0.867. We subtract a seventh. That puts us to 0.723. We add a ninth, puts us back to the right, and now we're at 0.835. We subtract an 11th, and that puts us at 0.744. Okay, and obviously this can continue on infinitely long, but I think what you're seeing is that this ball is starting to move less and less each direction, and it's starting to hover around a certain number, and that's the sum that we're interested in. Okay, if that happens, we know our series converges. All right, and I'm just going to show you that after 100 terms, that sum is 0.782898. After 101 terms, it's 0.787873, and we're about to find out that the actual sum is pi over 4, which is in between those two numbers. Okay, so seeing that, there are three things that have to happen, or three things that we need to show to have an alternating series converge. Okay, this is called the alternating series test. Number one, the limit of the nth term has to be 0. That has to be true for any series to converge, right? That's the nth term test, so that's kind of a given. But remember, this a sub n does not include the flipper. So we'll leave off the flipper, and we'll just look at what is the absolute value, basically, of the series doing. Is the absolute value of the series head towards 0? If yes, then we can move on to step 2. If no, then we're done. The series will diverge if number 1 fails. If you go back and look at this example here, okay, the limit of this sequence as you go to infinity is not 0, right? It's either 1 or negative 1. So therefore, this would fail the alternating series test after step 1. Okay, number 2. This says that every term of your sequence, this is not including the flipper now, okay? Every term of your sequence has to be a positive. Has to be a positive. Now, what's that mean? It means that you legitimately have an alternating series of terms that rotate between positive and negatives. Okay? If some of these a sub n's were negative, then you wouldn't necessarily have an alternating series. You might have 3 negatives in a row or 4 positives in a row, okay, depending on what kind of things are coming out of this a sub n. So the a sub n's have to be positive. And then the last thing we need to show, and this is the trickiest thing to show, and I'll show you 2 tricks to doing this, is that your terms must be getting smaller the farther you go. It says a sub n must be greater than a sub n plus 1. And that's something we'll need to show. There's kind of 2 ways that that's usually done. If all 3 of those criteria are met, then your series converges by the alternating series test. And by the way, there's some buzzwords that kind of go along with these 3 terms here that I'm going to throw in here. Okay, so basically you can say an alternating series will converge if the series is an alternating series of positive terms, okay, that monotonically decreases to 0. All right, so what are we saying? You're saying you have an alternating series of positive terms. That's number 2 here, right? You have positive terms that alternate between positive and negative. That monotonically decrease. That means each term is smaller than the one before it. That's number 3. And they have to decrease to 0 in order to converge. So that's kind of the sentence or the buzzwords that go along with those 3 things. And that's what needs to be verified before you can say that your series converges. Okay, so here's some examples. All right, we're going to go through the alternating series test step by step until we either find something where we run into a kind contradiction in one of the three steps, or we get all three to work. So first series here, we're going to first start by taking the limit as n goes to infinity of the nth term of the sequence, and this is without the flipper involved here. So in essence, this is the nth term test for divergence, and using L'Hopital's rule, we get this limit to be 1. So right now we're already done. This series diverges by the nth term test. It does not diverge by the alternating series test. The alternating series test is only a convergence test, but we can tell already that this series is going to diverge. These terms are going to get, or the sums I should say, are going to get larger and larger and larger. Okay, now how about this guy here? Start by taking the limit as n goes to infinity of the nth term of the sequence here. Cosine of pi n divided by n plus 1. Now, the numerator oscillates back and forth between -1 and 1. That's as big as the numerator can ever be. The denominator is going to get infinitely large. Okay, infinitely large. So this limit is 0. So far so good. Criteria 1 has been met. Now, let's write out a few terms of this a sub n to see what comes out and whether or not we always get positive numbers out of this thing. Okay, so if n is 0, we're going to get cosine of 0, which is 1, and in the denominator you're going to have 0 plus 1. So your first term is 1 over 1. When n is 1, you're going to get the cosine of pi, which is -1 over 2. So there we have a negative term. Now if there's only one negative term or a couple, that's okay, but if it's going to be always negative terms popping up as we go down infinity, then that's a problem. Let's see here. Cosine of 2 pi is 1, so we have 1/3, and this next term is showing me that it will be the case that these negatives keep popping up throughout the entire series, and that means we don't have an alternating series of positive terms. We have negative terms that keep popping up. Okay, so the alternating series test fails, and we cannot make any conclusion about this series yet. Okay, no conclusion is made. We don't say automatically it diverges. The reason I said the first one diverges is because it failed the nth term test for divergence, which we already had. Okay, let me shrink this stuff down because I'm going to need some more room. Draw group. Okay, now -1 to the n times 1 over n. Alternating series test. All right, number 1. Does the limit of the nth term go to 0? In this case, yes it does. 1 over infinity approaches 0. So far so good. It's very clear, and I'm sorry, this n should have started at 1, not at 0. Okay, it's very clear that these terms, okay, 1 over n is always going to be a positive number as long as n is a positive number. Okay, and n is going to be a positive number because it starts at 1 and goes to infinity. Okay, not much work to show there. Now, we've gotten to step 3, which means we need to show, okay, let me write this down. We need to show that for all n, okay, 1 over n plus 1 is less than 1 over n. That's what we need to show. And we can't just plug in a few values and say, yeah, no kidding, there it is. So let me show you 2 ways that this is generally done. Let me bump this over here. Okay. If the formula is simple enough, like this one is, then I'm going to write what I want to have, what I want to be true towards the bottom of my page. I'm going to work backwards until I have something that we already know is true. Okay, it's kind of cheating in a way, but you're working backwards from what you want. If you do some legal moves and end up with something that's obviously true, then the steps going down the page show that it is true. Okay, so let me show what I mean here. One legal move here, because these are both positive numbers, is to reciprocate both sides, okay, and to flip the inequality sign. Okay, that's a legal move. And then a legal move from here is to subtract n from both sides. Okay. So here you go. I have something that we know is true. 1 is greater than 0. And then if I just look at the steps going down the page, it makes sense. Okay, 1 is more than 0. I add n to both sides.
and then I reciprocate both sides but flip the inequality symbol, and I end up with what I want. Okay, that's kind of the backdoor way to do this. All right, the other way to do it, if it's not obvious and it's not a simple formula, okay, is to say, okay, let's compare our sequence with a function, okay, that is valid for all real numbers. Okay, so let's compare 1 over n with the function that it's behaving like, and the function's behaving like is 1 over x. Okay, so 1 over x is a function we can analyze for increase or decrease, and we do that with a first derivative. Okay, so the first derivative of 1 over x is going to be negative 1 over x squared. Okay, and our sign chart would tell us that f decreases, okay, from 0 to infinity. It also decreases from negative infinity to 0, but that's not important here. The only important thing is that what happens from 1 to infinity. Okay, so since f decreases from 0 to infinity, so does this sequence. And so that's the second way you can show that your nth plus first term is going to be less than your nth term. Okay, so one way or the other, that needs to be shown. And so therefore, this series converges by the alternating series test. Now, you're asking, do I have to show all that work? Well, if it's a free response question, the answer is going to be yes, you do. You have to show those 3 criteria are valid. If it's a multiple choice question and you think you can do it in your head, then you are more than welcome to try. But it's not always obvious that the nth plus first term is less than the nth term. Okay, so for your first part of the entrance ticket, go back to that first problem, test the endpoints of the arctan series. Okay, so I gave you 2 series that you would have to test using the alternating series test. Go ahead and do that, and then try 11.5 number 7 and 11.5 number 9 in the textbook, and that's good for both editions. Okay, now this is kind of a neat feature of alternating series. So I've written down here the series for sine x, which we know is x minus x cubed over 3 factorial plus etc. odd powers of x over odd factorials and alternating signs. In fact, I should have put in here negative 1 to the n. Excuse me for not doing that. Now, we know that if I plug in 1, that will give me the value of sine of 1, but if I cut off the series at some point, it's just an approximation. So the sine of 1 is approximately 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, which I've thrown into the calculator and gotten 0.8414, etc. The question that would be nice to have answered is, how good is that estimate? Okay, I have an approximation. Well, how good is it? Is it worth anything? Can I use it in a problem and be pretty close to the real answer? And the neat thing about alternating series is we can answer that question. Now let's take a look at a little visual here. Okay, and you already saw this a little bit with the arctan series, but you have your first partial sum, whatever it is, the first term. You add on your second term, and you now have your second, your S sub 1. I'll call it the second partial sum. Then your alternating series adds on a negative term. Okay, and so we go back to the left to get our next partial sum, but we don't go back quite as far as where we started. And then we add on another positive term, but that positive term has less absolute value than the one we just subtracted. And this goes on and on and on, back and forth, back and forth. Okay, and we saw how that lets you converge to a certain number. We may not know what that number is, and that's not important, but the point is that it converges. What this picture is showing you, I think, though, is that since the sum lives somewhere in here, okay, every time you add a term, you are getting closer and closer to that real sum, and you know how close you're getting. Okay, you are getting within the absolute value of the next term that's used. Okay, so in other words, if this was 3/5 that we subtracted, okay, and the next term that we're not using in our sum is 1/5, then I know that I'm within 1/5 of the true answer, because I'm never going to move 1/5 all the way past this s. Each time I go past, it's less and less and less. Okay, so what I'm going to write down here is that the error when you truncate off the series, okay, so I'll say the error using s sub n, the nth partial sum, okay, will be less than the absolute value of the next term in the series. Okay? So whatever is the first term that you don't use when you're adding these things up, the error has got to be less than whatever that is. And that's convenient to know for these alternating series. So for example, for this sine series, we got that approximation, 1 minus 1/6 plus 1 over 120 minus 1 over 540. The first term we didn't use in that series is 1 over 9 factorial, which is 2.75, etc., times 10 to the negative 6. Okay, very small. That's how close our approximation is to the true value of sine of 1. Okay, and here's verification. The sine of 1, take away my approximation, is 2.73 times 10 to the negative 6, which is less than 1 over 9 factorial. Okay, so when we approximate functions using an alternating series, we'll know an upper bound for how close we are, and that's very convenient in many applications. You try 11.5, number 29, which has to deal with this alternating series error, and that's all we have. Please email me 2 questions you have, and then we'll see you in class to work on the alternating series test.